do a little more Lagrangian mechanics, just to put that all into perspective. So now we had, just make this list here for Lagrangian mechanics. And I may have had this list here before. I just want to set the stage again. You have your mechanical system, and what's very important is you have to choose the correct or the useful set of coordinates that you're going to use. So I'll show you choose the coordinates. It really all boils down to having the right coordinates. That's a good start. Choose the coordinates, and then you construct L equals T minus U. Now with that last homework problem I'm talking about for next week, we already see we can have mixed Cartesian and circular, right, type of coordinates. So that goes under this choice of coordinates. And having done that, we have two things. We have the equations of motion. Will be qi dot minus dl dqi equals 0, I equals 1, and right, that's when you choose this, and you have this concept of generalized coordinates. And if L is not explicitly a function of time, then we have, from back in the variational calculus, we have a conserved quantity, dl dqi dot times qi dot minus L is conserved. So this is what we've inherited from the variational calculus so far. And we have to go through these things systematically. Okay. We have to systematically work through these things. And we've actually seen plane polar coordinates. So how we go to plane polar coordinates. And it won't take too much of the time right now. But we have to deal with this carefully now. Generalized coordinates in the Lagrangian. So, suppose we have the generalized coordinate is a function, no, other way around. Suppose we have a Cartesian coordinate is a function of these generalized coordinates, q1, qn. And our example is x1 equals r cos phi, x2 is r sin phi. Then our Q1, Q2 are R and phi. So how do we get the kinetic energy from this? Did we do this last time? With the general Aij matrix? With the triple sum? Let's see what we have there. Repetition is good. Yes, that one. Exactly. So yeah, that's what we're repeating. So we had that. Then we had L equals a half. So I did that calculation already. We want to definitely focus on this. JK, AJK, Q, QJ dot QK dot minus This is the generic form that we're so interested in. And we've already assigned a couple of things where we're going to find what this square matrix is. And if I didn't say it last time, I'm saying it this time. We can always make this array here symmetric. So we can always make AJK equals AKJ. And for theoretical calculations, it's good to make that assumption. We can always do it because suppose we have A12 equals something, right? And A21 is not even there. That can happen as we're building the thing. What we then do is we go A12 over 2, and then this one will be equal to A12 over 2. We'll just divide it in half and give each one half. And then it gives us the same thing in double sum. So yeah, in other words, you can always make this thing symmetric by hand, and we'll just use that assumption. So what we want to do is prove this. Or actually we want to take this we have as a proof from the variational calculus. We want to take that and see what it actually means, what it actually equals. What I'm going to prove is that that is actually the energy. So my next calculation, and that's what I'm going to do for today, then we'll turn it over to you guys. The next calculation is to do this construction using this object here and see what comes out. Good, so I'm going to erase all this stuff. This is what we did. We constructed this thing, and now we're going to construct that. Here we go. This is also a calculation we're going to see repeated a couple times in the course of the semester. So construct this expression here, I'm going to call star. We go, first of all, we're going to write, what do I have, J and K? We're going to do D, L, E, Q, I, dot. And that will be taking D, E, Q, I, dot of the first half, because there are no dots in the second part there, so of the 1/2 double sum J, K, A, J, A, J, K, which is only a function of Q, so the derivatives will only act on these. And when we do this, we've got J and K. We can go right through these and on Q. And then the derivative with respect to Qi dot of this, Qj dot, Qk dot, is going to be delta J or Ij. I'm just doing a product rule. Delta Ij Qk dot plus Qj dot delta Ik. And once we write that down and when the dust settles, what I did was I just applied this derivative to this product. I just did a product rule. But the partial of Qj dot with respect to Qi dot is either 1 or 0. If I equals j, it's 1, and if I is not equal to j, it equals 0. Has everybody had the Kronecker delta before? I think we all have, right? So that's where that comes from. It's the product rule. And now what we make use of is the fact that this Kronecker delta just picks off 1 of an entire sum. So when I is equal to j, Or I could put it so when J, summing over J, when J is equal to I, then I get the one contribution. So it collapses one of these sums. So the sum over J is gone. With the sum over K, I change the name of J to I, because that's the only one that's non-zero. No, I'm sorry, to change the name of I to IJ QK dot J over J IK. There we go. Missed that one. AIK QK dot. So that's the summation there. And the second summation, K gets turned to I. So J A J I Q J dot. Yeah, leave some room on this one. This is an important kind of calculation. And now I'm going to make use of the symmetry that I just invoked. So this is also, I can replace AJI with AIJ. So I would have QJ dot. Here I have AIK QK dot, so it's the same sum, because I'm summing over this index and this thing is tagged with A with I. And since the half plus a half, I get an entire sum over A by K Q K dot K equals 1 to N. So all of that was to get this going on. And now we have room here on the left. So now we have the sum over DL dQi dot times QI dot, sum over I. We just had the sum over K. AIK Q K dot QI dot. See how that one's that one right there? And now we're going to subtract L, which is, I'm subtracting a half of the double sum. And I can use I and K. J and K doesn't matter. AIK QI dot QK dot. So I'm subtracting off the kinetic. Minus a negative is going to be a plus U Q. So this object here is this thing here. And when the dust settles, this is twice the kinetic minus the kinetic. So this difference is the kinetic, and it's kinetic plus potential. So that's the mechanical energy. You would have never guessed that that's the mechanical energy, but it is. So equals E, that is to say we have E plus U. So yeah, this is a really important part of Lagrangian mechanics, that this is the actual conservation law. If you have this type of a Lagrangian, then you can actually cut to the chase and all say T plus U equals E. And it's only one equation, it's not always that big of a deal. If it's a one variable problem, you better use it because it's your first conservation law. Good, so that is where we stand now. So if we go back to my original list of 1 through 5 here, then point 5 was that you have this and it's the energy. It's the first of our conservation laws. And I don't want to take any more of time today, but that's where we'll stand next week. This is a great calculation for you guys to practice as well. because we'll see this a couple times in the course of the semester. We're gonna do a couple of these repeats of this, do the double sum. Good. So let's leave it at that, and then we'll start working our problems with the board. Hope I've left us enough time. Yeah, we still got a half hour. That's not bad.